All right, let's jump right into this. Welcome to The Explainer, where we take complex research, strip away the jargon, and break it down into clear visual steps. Today, we are fundamentally questioning our assumptions about advanced AI and robotic dexterity. Look, we've all seen the viral clips, right? Humanoid robots doing flawless backflips, autonomous systems that seem to understand the world perfectly. But beneath that really glossy, sci-fi surface, there's a fascinating and almost hidden vulnerability in state-of-the-art robotics. To really understand this vulnerability, let's ground it in a physical reality we all deal with. Imagine you go to pull open a kitchen drawer, but it's kind of stuck. The runners are jammed, or maybe it's just overloaded with heavy utensils. What do you actually do? Well, you instinctively adjust your grip, you pull a little harder, maybe you brace yourself against the counter. You naturally adapt to that physical resistance. So it begs the question, why do million-dollar robots absolutely struggle to open a simple, sticky drawer?
It's wild, because while these highly sophisticated robotic arms look incredibly capable, physical tasks like pulling a stubborn drawer often cause state-of-the-art AI to just completely collapse. The robot might successfully grasp the handle perfectly, sure, but the very second the physical resistance, the contact load changes, the hand slips, the grip breaks, and this million-dollar machine fails at a task that, quite frankly, a toddler could manage without breaking a sweat. So here is our roadmap for figuring this out today. We're going to cover 1. The dexterity illusion, 2. Moving articulated objects, 3. The DragMesh-2 framework, 4. Training without touch, and finally, number 5, testing under pressure. All right, let's kick things off with section 1, the dexterity illusion, basically how AI is faking success. So it turns out a lot of AI models are essentially cheating in the lab. Their reinforcement learning takes a massive shortcut. First, they train under these fixed, perfect lab conditions, where the only thing that matters is task completion. Just get the drawer open. As a result, the AI overfits to those pristine conditions by relying on max power, highly saturated actions. It basically just yanks the drawer open as hard as it physically can because, hey, in the simulation, there's no friction, right? Nothing is jammed. But step 3 is the brutal reality check. The moment real-world resistance increases, that brutal policy just shatters. The robot's hand detaches from the handle. Because, as it turns out, success in the lab absolutely does not equal stable physical contact in the real world. Moving on to section 2, moving articulated objects. This is the core physics problem. Think about this. Why are doors and drawers so much harder to deal with than just picking up a block? When a robot manipulates the static object, it can just clamp down and directly dictate its position in space. Easy. But articulated objects, totally different beast. The robot cannot directly actuate or command the drawer itself. Motion has to emerge entirely through sustained physical contact between the robot's hand and the object's handle. You can't just type a line of code telling the drawer to move 10 inches. Naive strategies that try to just replay a geometric trajectory always fail here because they completely ignore the actual real-time friction and physics required to drag that specific physical drawer. It's honestly fascinating to look at what it takes to actually do this right. For a robot to successfully open a drawer, it demands this hyper-realistic, physically compatible coordination. We're talking multi-finger contacts, constantly adjusting and reacting to the moving part of the object on the fly. The hand has to stay glued to the handle throughout the entire arc of motion, without slipping or breaking its grip even for a fraction of a second. Which brings us to section 3, the DragMesh-2 framework, the researchers' breakthrough solution to all of this. When we break down the DragMesh-2 architecture, the biggest, absolutely crucial takeaway is that the AI policy controls the hand and only the hand. It has zero direct control over the object itself, which means the target joint, like the door hinge or the drawer slider, has to move strictly through real simulated physical interaction. To pull this off, the framework leverages these temporal awareness and physical causality modules to constantly monitor and evaluate the entire history of the physical interaction. And the real engine driving those modules is something the researchers call PICA. That stands for Physically Informed Contact-Aware Training. Now, instead of just giving the AI a high five for eventually getting the drawer open, PICA actually injects observable physical signals right into the learning process. It actively penalizes the AI if its grip slips or if it tries to cheat by using dangerously high maxed-out force. It essentially forces the robot to recognize the signs of its own hand detaching, steering it completely away from those brittle shortcuts and toward genuinely stable, robust behavior. All right, let's hit section 4, training without touch. This is where the magic really happens. So you're probably wondering, how does Pika actually know the hand is slipping if it doesn't have a sense of touch? Amazingly, this whole system requires zero tactile or force sensors, which, let's be honest, are notoriously fragile and super expensive in the real world anyway. Instead, it relies on the history of its own movement tracking errors. Imagine you tell your arm to move backward 10 inches, but because the drawer is stuck, your arm only actually moves 2 inches. That discrepancy? That's a tracking error, and it's a highly observable mathematical signal. By analyzing the history of these errors alongside the commands it just sent, DragMesh-2 can literally predict if its palm is starting to separate from the handle. It calculates its own detachment risk just by noticing that the physical world is fighting back against its commands. It's implicitly feeling the contact load without actually touching it. It's brilliant. And to train this incredibly smart system, the researchers didn't spoon-feed it human demonstrations. Nope. They built a massive data set heuristically, pulling directly from 3D geometry using the GAP-PartNet database. By reading the geometric annotations, like where a handle is located and exactly what type of hinge it has, they generated these pure geometry reference trajectories just to initialize expert graphs. The AI uses that basic geometric baseline to understand the scale of the motion, and then it figures out the actual complex physical contact dynamics entirely on its own through pure trial and error. Which brings us to our final section, number 5, testing under pressure. Let's see what happens when the real world pushes back. The researchers really put this to the test, benchmarking DragMesh-2 across 7 different GPartNet objects. Now, generalizing between a microwave door and a heavy cabinet door is no joke physically. One has a shallow, lightweight hinge, the other is a heavy, sweeping arc. But because DragMesh-2 is so hyper-focused on the local physical contact dynamics of the handle itself, it generalizes beautifully across all these completely different types of hinges and sliders. Okay. Here is the data-driven climax. The researchers threw these models into what they call an out-of-distribution shift, which basically meant cranking up the physical damping or resistance by 4 times. At this extreme level of resistance, competing models like the highly advanced transformer PPO just completely collapse. I mean, they drop to a dismal 0.09 success rate. Their rigid little shortcuts instantly break. But DragMesh-2, it maintains a highly robust 0.56 success rate under that exact same intense pressure. It succeeds precisely because it actively senses the resistance and automatically adjusts to maintain that physical contact. But check this out. The data also reveals a fascinating anomaly that kind of flips how we normally think about machine learning. Look at the relationship here between training length and success under high resistance. When the base model is trained for 150 epochs, it scores a solid 0.55 success rate at 4x damping. But if you train it longer, say 300 epochs, its success rate plummets down to 0.10. No way, right? Why would more training make it worse? It's because optimizing for too long on standard, easy tasks actually destroys its robustness. The AI gets lazy. It over-optimizes for a perfect world and drives itself into a highly saturated, brittle state. It just goes to show, simply training longer doesn't magically build physical robustness. You need a fundamentally smarter framework like Pika to keep things stable. All of which leaves us with this final, genuinely provocative thought. Right now, DragMesh-2 brilliantly solves the problem of a floating, dexterous robotic hand pulling open a heavy door. But the researchers point out in their future work that these contact trajectories extend way naturally beyond just the hand. Think about it. If an AI can learn to feel resistance without sensors and maintain perfect adaptive contact while pulling a heavy stuck drawer, how is this mastery of upper body dexterity going to translate when it's attached to a walking robot? When we finally couple this flawless, intuitive contact interaction with whole body control, how is that going to unlock the future of humanoid locomotion? These robots are literally learning to feel the world's resistance, and they are figuring out exactly how to push back. Thank you so much for joining me on this explainer.